Yeah. Fantastic. Yeah, thanks again for having me. I'm going to tell you today about a collaboration between, well, a bunch of people. So this would have possibly about fantastic collaborators. Let me first thank Tibor, who just moved to Budapest, Nico, who is a lecturer in Bristol, Grace, who is a PhD student of David Hughes in Princeton, and Vedika in Stanford. And well, this started actually with me, Nico, chatting about spin glasses in code theory, and Tibor and Vedika kind of independently, of course, doing a lot of work on that over the last 2 years. And then actually it was Shivaji, whom we also should thank, Shivaji Sondi in Oxford, who brought us together to chat, and then this is what came out of it. And okay, this is what I'm going to tell you about today. There's also 2 papers on the archive, and it's the second one that is called Topological Quantum Spin Glass Order, and its realization in good LDPC codes. And maybe, okay. Let me start with maybe a trivial statement, but which makes the point of why kind of information science, and in particular error correction and kind of statistical mechanics and the idea of classiness are related. And this is just that, okay, one of the tenets of StatMech is basically that systems equilibrate and are well described by statistical ensembles. And that of course means that equilibration is a loss of information, right? So regardless of how you start and how you initialize your system in the North Pole, given recent developments, and now the steady state of that system is independent of the outcome, is that at long times, there's no ice. And so if you was to encode a bit of information in the presence or absence of an iceberg, you would be in bad luck, right? So and that of course is just to say, if you want to store information, you have to avoid equilibration. Okay, so far, so trivial. Now, okay, how do we do this? We do this with an analytical process called error correction. And there's multiple ways to do that. So one way is active error correction. This is, for example, what people are doing right now in quantum computing. For example, here is a little sketch of what Google is trying to do. So Google has this beautiful chip. And this is not the current one because they don't release pictures anymore. But once upon a time, this was the chip. I think was this where Adam, where you ran some stuff? Maybe. Also on the new one. Also on the new one. Okay, fantastic. Very good. So Adam knows them all. But okay, so this is a picture of the old chip. And then what you do is basically you want to measure some properties of the system, which gives you an image somewhat like this. And then you give a quantum computer, some classical computer, actually the task of connecting up this dot in a particular way. And this gives you an idea of a feedback to give to your actual system to preserve the information. So it's kind of an active, you extract entropy, you process the information that you learn, and you feed back into the system, kind of stabilize in a highly non-equilibrium state. That's the idea of active correction. But what would be much nicer, maybe, is if we had like passive correction, which is you just put your nice little chip in a bathtub full of ice, and it's happy even in the presence of some errors. This is of course what happens in like phases of matter, right? And this passive error correction is actually the topic of this talk, because I'm interested in an equilibrium physics of particular spin moments. And okay, so how do we get memory? So what's the connection to condensed matter precisely? And one way to see it is, okay, is memory by symmetry breaking? That might be the most common form of symmetry break that we see in condensed matter. And there's active error correction. And for example, classically, a system that requires active correction is the 1D Ising model, which famously does not have a finite temperature stable ordered phase. But what you could do is you could periodically in time ask, oh, how many ups and downs are there, and just reset the system to whatever there's more of. And actually you can show that this actually, as a non-equilibrium process, can stabilize kind of an all up or all down state. In contrast, the 2D Ising model, or the 2D repetition code, if you're a computer scientist, actually is a passive memory. So if you are below a critical temperature, you just have to cool the system, and you will stabilize kind of dependent on the initial state, you will stabilize a positive or negative net magnetization for an exponentially long time in the system size. This is kind of what I mean by passive memory. And okay, the topic of this talk will actually be quantum memories, which are much harder to come by as of now. And where you want to stabilize not a classical bit of information. So here, for example, right, you want to classify basically the ground states of the easy model by being all up or down. So you have two different kinds of states. And you can, for example, store the classical bit in the information of whether your magnetization is positive or negative. Quantum mechanically, what you want to do is you want to stabilize a quantum state. And then there's a 2D toric code as an active procedure. And actually, one big open problem in quantum error correction is whether there is a low-dimensional analog of the 2D Ising model where you stabilize kind of passively quantum information for a long time. But in 4D, I can tell you there is a solution because the 4D toric code, certain 4D generalizations, sorry for the weird sketch, the best I found so far. Actually, the 4D toric code would have passive memory. And if you now look at the numbers, if you do some numerology, you see like, oh, that goes from 1 to 2, and this goes from 4 to 4, and this is actually not an accident. Because what we will see hopefully later is that you can go from classical to quantum memories via products. And the easiest product that you can do is a Cartesian product, and this will double the dimension. And actually, these models are precisely related in this way. As I will show later, the 2D, 1D Ising models, the Cartesian product is actually the toric code in a well-defined way. And the 4D toric code in the same way is, in a well-defined sense, the product of two Ising models. And actually, the thermal stability, the absence or presence thereof, is directly inherited from these input models. Okay, so this is symmetry breaking, right? So actually, maybe I should say, what is this history with symmetry breaking? Of course, maybe this has been an example of spontaneous symmetry breaking to the Ising model for the longest time. This is, of course, in condensed matter theory known as topological order, which has been now reinterpreted in recent years as the spontaneous breaking of higher form symmetries. But for a long time, this was basically seen as something that is beyond, like, at least the standard Landau paradigm of spontaneous symmetry breaking. There's one more way to go beyond symmetry breaking in some sense, and that is via glassing. So symmetry breaking leads to non-trivial dynamics. This is in the end what we are after. And in some sense, the idea of glassing is that you get non-trivial dynamics without the onset of any apparent order. At least this is what motivated all the study from an experimental point of view, right? So cool down, for example, some liquid, and without the onset of a crystallographic structure, kind of you see some slowing down of the dynamics. This is another way to get a memory. And okay, for example, maybe the simplest model of a glass is something called a P-spin glass, for example, which looks something like this. You take a Hamiltonian on some n spins, and you choose some extensive number of random 4 tuples. So you group spins together in groups of 4. And then these groups define a 4-body interaction. And you make all of them ferromagnetic. And if you do that, you can visualize this on a graph where kind of the bits or spins are kind of indicated in blue, and the checks or interaction terms are indicated in 4, indicated by the red squares. And this is some biregular graph. And this is just a visualization of the model. And what you will find is that this thing looks like a tree locally, and then connects up after some point in some random way. And you can actually show rigorously, actually, that this model has a property called linear confinement, where the energy landscape looks something like this. So you have many ground states, right? So one ground state of this model is actually very simple. It's the ferromagnet, right? This is the ferromagnet after all. But actually, there's many, many more ground states of this model, many more spin configurations. And you can show that they are separated by extensive energy barriers. And what you can also show is that there are exponentially many of them. And then further, what you can show, actually, is that there's also many local minima. And this really gives rise to this kind of phenomenology of classes, where if you cool them, because actually most of the kind of stable minima they're stable because they're separated by extensive energy barriers. Most of the stable states are actually in local minima, and then if you cool, you get stuck in one of them, and you're toast. And then you get some non-trivial dynamics if you don't see the onset of ordering that you might see if you end up in one of these ground states. And of course, to connect to maybe what we saw before, right? The crucial thing why this is kind of beyond symmetry breaking is because the local and global minima, of course, they are all dynamically stable, but they are not related by symmetries. Right? So in that sense, it's clear that you cannot describe it in the same way as, for example, the 2D easy model. So I advertise products. So what basically, if you don't remember anything else from this talk, what you should remember, hopefully, is that you can take a product of these kind of models, and then you get something very new, which is topology, what we call a topological quantum spin glass. And this is basically the Mount result. And it is okay, you take the basically Euclidean or Cartesian product of this graph in the same way you get from the 1D Ising model to the 2D Ising to the toric code. Sorry, you take the same product and then you get some geometry that looks like this. So it's not easy to draw because it's something called a co-boundary expander. But what the upshot is that kind of it's some surface that folds out in all directions. So it's a bit like if you think of the surface generalization of the tree. Just like two lines, the Cartesian product is the sheet. The Cartesian product of two trees is something that folds out in all directions. And then again, you can basically do the toric code construction. That is, you could qubits on the links, and Z and X stabilizes on the faces and vertices respectively. And you can also show that this inherits actually the landscape from this parent model. This is now then something that is called linear boundary and co-boundary confinement. I will explain what that means. But now each of the minima, right here, each minimum is associated with kind of a minimal energy, with a local minimum configuration, right? So now dynamically, you could encode in each bit, you could encode like a classical sequence of information in some finite number of bits, of course, because you have more than two states. It's not only one bit that you encode, but the information that you encode is fundamentally classical in the spin glass. But in this system here, the information that you encode is actually quantum. And these models are topologically ordered in a well-defined sense. And in particular, what I will hopefully get to show too is that each kind of state that is dynamically stabilized in one of these local minima is non-separable. So it's topologically ordered in some well-defined sense. That is, you cannot prepare the state by some local, finite depth local circuit. This will be kind of the definition. Yeah. So if you remember nothing else, please remember this.
So in the classical case, you can count minima. So
yeah. Now you can't.
You don't know for
well, I mean, it's a continuum, right? Because you stabilize a qubit, which has phase and so on, right? So it's really some
because you draw it like their counter. So
yeah. I mean, I don't know how to draw. It's really some.
Okay.
I mean, I will make precise what this will mean. But it's basically, there's some n-dimensional density matrix that is stabilized, really, that is global, because you can have superpositions between kind of all these positions. So if you want this loop soup is a continuum, you can think about it like that, maybe. Yeah, I don't know how to draw this. Sorry. But yeah, you're right. It's some qubit that you stabilize. Obviously, it's not countable. You can count the dimension.
Yeah.
So this you can, in this sense, it's countable. Okay, what's the plan of action? To understand why this happens and what is actually what we're doing, and maybe even how you prove these statements. So I will first talk about the structure of Gibbs states, classical and quantum, and this will get to John's questions of how exactly kind of the steady state looks like. Then in part 2, I will tell you how spin glass order, how you can get spin glass order actually directly from kind of results in computer science by something called linear confinement. And then in part 3, I will show that if you do this product construction, you get basically the same but topological. So this will be the plan of action. Okay, think Gibbs states. So how do we formalize statistical mechanics? One of the central ideas of kind of all these dynamical non-triviality is that the Gibbs state, which is e to minus beta e, ceases to be unique. And the standard way of doing this is the Peierls argument. or is the Pyle's way of doing it, which tells you, okay, you take different boundary conditions, for example, here for the 2D Ising model, and then you get a different result. So one way of saying the Gibbs state is non-unique is you say, oh, it depends on the boundary conditions. And in the 2D Ising model, this will be true below TC and not true above TC. There's different ways of studying the thermodynamic limit. We will do something slightly different here, because this is very, very hard to generalize to kind of the models we're looking at. We look at something different. We will ask, can we dissect configuration space into different subsets? Here, for example, V1, V2, V3, that are surrounded by so-called bottlenecks. And what does it mean? So you have configuration space, which, because this is like a sketch, right? So this is like some high-dimensional thing. I project it into 2D. And you say, okay, let me choose some subsets, and then let me choose a boundary of these subsets. For example, right, you take this in the 2D Ising model, you could, for example, take the spins with positive and negative net angulation. These would be two sets. Right? And you ask, like, okay, now the boundary is like, oh, coming from the set, you flip some number of spins, right? This gives you a distance, a metric on the space. And you can talk about boundaries and subsets. And now you can ask, okay, the Markov chain bottleneck theorem tells you if you have a dynamical process that is described by some Markov chain, you can actually bound the time it takes to escape from like some set by the relative weight on the boundary. In particular, if the boundary has much less weight in equilibrium than the set itself, then the mixing time is kind of strongly bounded. So you can actually define a non-trivial phase by the fact that you can do this decomposition into different subsets of configuration space. And this is basically directly a statement about dynamics coming from thermodynamics. Because you say, okay, you calculate a property in equilibrium because of the bottleneck theorem. It tells you something about basically arbitrarily local dynamics, which have this thermodynamic state as its steady state. It might be a technical, but how it has to go. And okay, yeah, therefore the 2D Ising model, for example, just to give an example, you can look at, okay, at a particular temperature, what's the distribution of magnetization, right? And then above TC, right, it's basically some distribution around 0. And below TC, it's bimodal, right? And then you say, okay, so I take the subset that is some configuration, all configurations around the equilibrium magnetization, but then I can do 2, and they're separated by a region of very, very low weight. And this is really what we mean. And this is one way to prove that this bit that you store in the Ising model is stable for exponentially long times in system size. Okay, so then you can show with a bit of math that now if you look at arbitrary dynamics actually, and you have a decomposition of your state, of your configuration space, then any steady state of any dynamics kind of in general is some linear combination of kind of so-called extremal states. So actually what you can show is that, maybe more formally, what you can show is that the steady states of local dynamics, they form a convex set. And okay, convex set has extremal states, which are, for example, in the Ising model, there's 2, or up or down, and any steady state will be kind of some linear combination of these 2. So this is really all I'm saying, right? And then in general, kind of your classical memory basically means that you are preserving kind of the prefactors here. So you preserve some classical probability distribution. This is really what we mean by saying we have a classical memory. Well, this is what I would do, at least. Right? And then the Ising model, for example, there's 2 Qs, they have to sum to 1, right? And this is stable under kind of exponentially long times. Okay, so how does it work in quantum? So for quantum, it turns out there was until last year there was no actually analog of the bottleneck theorem. So actually, the first thing that we had to do is to generalize the Markov chain bottleneck theorem to quantum channels. And this was done by us and also more or less simultaneously by a group at MIT. And okay, the idea is the same. Now you have not a configuration space, but a Hilbert space. You take a subspace, not a subset of configurations. And you get a slightly different bound, but essentially the statement is the same. You look at the subspace, you ask, okay, what's the subspace of Hilbert space that I can reach by applying kind of local operators? So now the distance metric is, or you start from a state, and you want to apply kind of operators with limited weight, so acting on few sites. And this will give a definition of a boundary. And then you say, okay, how often do I have to apply a quantum channel to get out of an initial state that is inside the subspace? And okay, actually, what's interesting, you get like slightly weaker bound. So actually, this is some Schatten 1 norm. And then if you translate it into directly the weight in the same sense as you would in the classical Markov chain bottleneck theorem, you actually get a square root here. So trace, well, this is a projector onto the boundary. This is the set, right? And in classical bottleneck theorem, there is a weight of the boundary divided by the weight of the set. And here there's a square root. So actually, tunneling does help you. Right? Because why is it non-trivial to prove? It's non-trivial to prove because an energy barrier, right? Just because you have low weight, that doesn't mean in quantum mechanics you literally can't go through it, right? You can tunnel, but tunneling only gets you so far, and this is basically the statement, the non-trivial statement here, and that kind of tunneling, at least in this case, only gives you basically a square root, as we got. And then again, you can ask, okay, so what does a general steady state look like of a channel? And it looks, okay, now the steady state obviously is a density matrix. And now the decomposition works slightly similar, slightly different, right? So as you have a classical kind of distribution over density matrices, but the density matrices factor into a tensor product, where this kind of depends on the exact decomposition, and this mu I is actually arbitrary. And this is basically a qubit. But in the Foley-Torre code, for example, basically this would be some, well, I think 8 or 4-dimensional, depends, I think, on the exact definitions. Some finite dimensional density matrix of some qubit. Right? But in general, actually, there can be more than one quantum memory. Right? So this is why you have also a classical sum. So if you want to think of this, is okay, you have a sum over quantum memories. So each I is a single quantum memory, but you can have multiple. And then you can also ask, okay, in what quantum memory did I actually encode my qubit? So this is the general structure of steady state. I hope that this answers your question of how you.
Oh yeah, I know about this. Yeah.
Yeah. Okay. Fantastic. Okay, and then you can characterize.
I make a statement on the result before. So, in general, this breaking over conditionality will happen in some large size limit of something we have.
Yeah, exactly. So right there is a. I mean, this is a system size dependent quantity.
So,
right.
In general, what you have therefore is not, this breaking of the Gibbs measure, but you have what we call metastability. And I say because we've written papers about this. And this steady state manifold that you're writing is really a metastable manifold, in which fast degrees of freedom have relaxed, and then for very long times you live remembering these initial conditions. And in the quantum case, I think you can have classical metastable states or quantum metastable states, exactly as you said.
Yeah.
But over time, these for finite systems will relax.
Depends on your order of limits, basically.
Yeah. So
So
there has to be a
system.
there has to be a separation of time scales.
Yeah.
Which I guess will be important in practice eventually.
No, of course.
Okay.
And what I mean. So yeah. So in the example that we're interested in, this will kind of be some exponentially. The expectation will be some exponentially large system size. So there is like a very strong separation. But you cannot think about power laws or logarithmic things or whatever. Not. I mean, so that then, and then of course, and then what you call kind of a non-trivial phase and whatnot maybe depends a bit on your definition.
Yeah. Because that's it's more characteristic of classes, slow and no metastability rather than true symmetry rating. But that's another discussion.
Yeah, okay. I mean, it depends a bit what you mean by true. When do you call it true? I mean, it has to be exponential in L and N.
Yeah, not true. Depends on the but you will have a finite. There are two situations. Either you have time scales that they scale with system size, exponential, and so on, and those very quickly go to infinity.
Yeah, you could also have a one time scale, but that's not the case here.
Or you have very long time scales that don't go to infinity, or you have them exponentially going to infinity, but your system sizes are finite.
Yeah.
And
so
then you're eventually thermodynamic. Okay.
So what I would mean if I say there's a non-trivial phase is that there's something that depends on system size.
If you take the limit, goes
if you take to n to infinity, there will be a separation. So if you take system size 50 first, then time to infinity, it will be okay. Right? And metastable, I would call it there's some parametrically long thing. Or maybe superlinear or whatever. Okay. Yes. And okay, so what we will call spin glass order, and there's many, many different definitions, so please don't jump on me. But what we will ask, okay, does the number of components grows exponentially with n? So we want that there's many, many different components, aggregate components. And are there any components that contain ground states? Right? And the answer to, and here the answer should be yes. And here the answer should also be yes. So you want that there's many components and you want that most of them are local minima. This is what I will want, what I want to have. And then also what I will want is I want topological order. And you can, for that, you can, for example, ask, does the system preserve quantum information? Or are the Gibbs state components long-range entangled? And what I want to tell you is that for certain QLDPC codes, so for certain variables based on quantum error correction, the answer to all of these questions is yes. So this is basically what I'm going to show. Okay. How do we get there? We know maybe formally what is actually what we are showing. Okay. So classic linear codes. We start from error correction. And if you're a computer science and a physicist, you use a very different language. And you will switch a bit, and I hope it's okay. But please interrupt me if you get lost. So we start with something called the Hamming code. It's an example. In general, codes in computer science or linear codes are defined in terms of a binary matrix. And in this matrix, each column corresponds to a bit or a spin 1/2, and each row corresponds to a constraint or an interaction term, right, that you want to minimize. This is one possible constraint, right? And this is generally this is called the parity check matrix because it defines parity checks. And we can translate this into a ferromagnetic Hamiltonian, which is just basically written as a sum over rows. And in each row, you take this product of spins where you have ones in the matrix. So there's a one-to-one correspondence from a parity check matrix to a ferromagnet. And the energy of the spin Hamiltonian is actually given by, if you take a vector, x, right, which is a binary vector, this is, you can refer to this as a spin state, right, up or down, it's 0 or 1. You have to translate a bit again between pluses and minuses and zeros and ones, I'm sorry. But there's a direct relation between kind of the weight of the image under this matrix. So you do matrix value application, and this tells you which constraints are violated, right? So you do the matrix product x times h, and you ask how many ones are there, and this is actually the energy of this easy model. So it's very, very simple. So in that sense, these are very special easy models in that sense. Right? Because they are linear. And then in code theory, we characterize such a code by 3 numbers, that is nkd. And n is the number of spins or bits. K is the number of logical bits, which means that this Hamiltonian has 2 to the k ground states. In this case, for example, it's 4. And then there's a distance d, which asks, if I want to go from one ground state to another, how many bits do I have to flip? And of course, in error correction, I want to have many because I want to be able to correct a lot of faults. The environment will kind of flip spins. And I want to go back to the state that I had originally. And okay, in general, then what we will do is we will consider families of models, right? And then you want to ask about the scaling of KDN and maybe energy barriers. Okay, so now there's a special class of codes that we will look at that correspond to kind of mean field models of classiness, which are called good codes. And we'll especially say good low density parity check codes. And what does LDPC mean? Yeah, low density parity check. Every check involves finitely many bits or qubits, and each qubit is part of finitely many checks. This just means it's a sensible Hamiltonian, right? So it's like finite spin interactions, right? And the energy is extensive. This is really what you want, right? So LDPC codes, if you're a physicist, this is what you want to look at.
Did you say mean field?
But it's mean field in the sense that it's like kind of an infinite dimension. So
anyone with anyone could be.
Could be also, and this would not be LDPC, for example. So maybe I shouldn't say mean field models. Forget what I said. I shouldn't have said.
No, well, mean field in the sense you don't have a lattice structure where they interact. So
They say if you don't have Euclidean
The
lattice structure,
multiplets that you choose to interact could be anyone with.
yeah, exactly. So you don't have some geometric
Yeah,
locality in Euclidean space.
yeah,
So you could be in hyperbolic space, and
Yeah.
it could be actually a very nice metric and everything. So in this sense, mean field is maybe a bit of too much. And okay, now a good code is something where k and d scale is n. And this is very, if you think of it as a physics model, right, it's very strange, right? Because you say, oh, there's exponentially many ground states, extensive ground state entropy. But also, if I want to go from one ground state to another, I have to flip a finite fraction of all spins. And this, of course, now starts to look a lot like spin glasses and glassiness in general. But, as Sean said, so then you can't do it locally on the lattice. In this sense, that's a neat field. But you really should say, okay, this has to live on something called expander graphs. An expander graph looks something like this sometimes it's different. With one example. And what you really mean by is you look at a set of spins and you ask how many neighbors does the set have, and you want that the number of neighbors kind of grows with the size of the set. And this is different in Euclidean space, right? There you would have like not the size of the set, but the size of the set to some power. But in 2D, you have a square root there, right? And the perimeter of a set is as the square root of the number of sides in the set, right? An expander graph means that there's kind of there's a finite surface to volume ratio. This is really what we mean. Okay, and this is what we look at. So how do you build such codes? I already gave one example, and this is really you take a random sparse matrix, which is basically the construction I gave on slide 3, and then you can prove a bunch of stuff. So you basically choose like kind of random tuples, and then you can show actually, okay, H as n goes to infinity has full rank, which means that all the checks are actually independent. So you can actually get the k for it just by counting. Very nice, very well behaved. You know, these models are then exactly solvable just because you can basically get most of its properties just by counting. And you can also show, and that's maybe the more remarkable statement, I don't know what is more remarkable, both are remarkable. And H is a good code. So this is exactly what we want to have. And in the spin glass literature, these are called p-spin models. So these have been actually known for a long time. Although fascinatingly, Gallagher got to them much earlier. And the other example is Tanner codes. And these are also very, very old. And they are basically what you do is you take an expander graph, then you maybe do a construction that reminds you maybe of a bit of a lattice gauge theory. So you have like checks on the vertices, and you put bits on the edges. But the constraint becomes more complicated. You put the constraint to be a local code. So instead of just saying, oh, the parity has to be even, like in Wegner's lattice gauge theory, you make a more complicated constraint. You say, oh, there's 7 incoming bits. And for instance, these 7 incoming bits should form code words of the Hamming code. Right? And then if you think about the Hamming code as distance 3, so if you flip like one adjacent bit, you have to flip 2 more to make the local check happy. The excitations kind of have to split and proliferate. And this again, if you, in a certain circumstance, you can show that this also gives you a good code. And in some sense, this actually looks quite nice, because this you can actually really build on like very nice hyperbolic tilings and so on. This can be highly symmetric. There's no randomness here. So this is just why I'm mentioning this. This doesn't have to be kind of some crazy p-spin glass. Yeah, very nice models. And then the remarkable thing is that in 1996, Sisters Spearman proved that these models generically have linear energy barriers. And really what they proved is that if I flip a number of spins that is less than some critical fraction of all spins, starting from a code word, then actually I violate a number of spins that grows linearly with the number of spins that I flipped. And this just really means it's a linear energy barrier. And this is a rigorous proof again that kind of gets you can get there relatively easily by counting. And of course, this gives you, for example, then immediately also the distance, right? If the energy grows, you can't go back to ground state, so the distance is already linear. And this is very unusual if you think about low-dimensional systems, where the barrier is really not linear, but typically something like a square root or something like this. Okay. Linear barriers immediately imply bottlenecks. I don't want to go too much detail, but basically, okay, right? You know basically that if you take basically a ball and like a finite region around your code word, right? Then everything that lies out has to be extensive this will be much higher in energy, and hence the wave is suppressed. That's kind of the upfront. Maybe it's not so surprising that extensive barriers lead to free energy barriers, basically.
So linear barrier is in the number of flips.
Yeah.
So the barrier scales with the number of flips. Now,
No, so the energy scales with number of flips.
the energy that you're climbing up scales with the number of flips. Okay.
Exactly. And also
If the
expensive
volume-
number of flips.
Is the volume of, so you're creating some excitation and it's growing like the volume.
Yeah, exactly.
Okay, okay.
Yeah, exactly. And this is of course somewhat related to the fact that your graph has a finite distance to volume ratio. Except the volume
How
ratio.
slow you are will depend on how far you have to go until you flip to some other state.
Exactly. But it will be something that's exponential in system size, right? Because the free energy barrier is necessarily expensive.
Okay.
Because entropy, I mean, basically, right, the energy grows extensively, right? The entropy can at most grow extensively, but has a prefactor that is the temperature. So at some temperature, the entropy is going to lose. But that's really the argument. It's really trivial, basically, once you read Simpsons-Spearman. Okay. What you can then finally do is you can count also how many states there are, right? I told you in certain models there's no redundancy, so you can get actually the density of states by looking at, okay, how many ways are there to violate certain spins? And then you can, okay, this can be exactly computed, the Z, right? So what you want to look at, you want to look at PG. So the global Gibbs distribution looks something like this. It's a sum over different components, right? So each VI is now some minimum. And now you ask, okay, I sit myself at a certain energy or a certain temperature, then I'm in some energy window. And it turns out if you now look at a certain state here, expansion actually allows you to bound how many spins you can flip before you leave this energy window. Right? And you can use that together with the fact that you know how many states there are in total to upper bound the number of states in one particular well. And if you do that, okay, you do some math and you ask, okay, how many states are there? And you say, okay, see that this actually grows with temperature. So as you increase the temperature, more and more local minima, or more and more distinct ergodic components contribute. And this is exactly what you want in the class, because that means if you cool, you will kind of see this gigantic number of local minima, and you will get stuck. So this is then the second part. Yeah, and for the expert, this is actually a lower bound on the configuration entropy or complexity of this full model. Okay. So what we wanted to show, so what have we shown? Basically typical states below TG, some critical temperature are surrounded by a bottleneck. That's basically what you can show by this. And then there's some number of distinct Gibbs states. These are the number of distinct minima. And this actually grows exponentially with n and exponentially in t. Right? So the prefactor of this exponential growth in n grows with the temperature. There's much more local minima than global minima. So the only thing that's left is to show what I said in the beginning, is that I have to show you that these kind of local minima, or these typical extremely Gibbs states in a more formal language, are not separable, so the topological order. Well, and I have to show you how to get all the 1 and 2 in a quantum system. Okay. I have, how many do I have? 10? Sorry? 15? Oh, wow, then I'm doing very well. So, okay, great. Okay. So how do we get to a quantum generalization of what I just told you? Right? So the first thing you could do is you could stick your your spin glass into a transverse field. And this is what people often call quantum spin glasses. And in some sense, the model that I want to tell you about are even more quantum than that. So what happens actually if you stick it into a transverse field? Right? So in a classical model, right, you have like distinct states living in different energy wells. And now if you include a transverse field, what you will do is you will actually mix the classical states. And actually what you will get is eigenstate localization. So that's interesting, right? And has been studied for a while. There's an old paper by Antonello Sghericcio and collaborators, which does it kind of in a maybe more heuristic way. And actually, then Andy Lucas, with that, a lot of parallel work on this actually, and all the things I'm telling you about. I had a paper earlier last year where they actually rigorously proved the statement using actually the whole machine of classical and quantum LDPC codes. And basically, what you can show is that eigenstates are localized in a well. So in some senses, this is not ETH. But of course, what this also means is that you can't really have stable superpositions between wells. So it's a quantum model, right, which now mixes, and these states are volume laws and whatever not. And you get localization, which is interesting. But what it is not, it's not a quantum memory. So this is still a classical memory, right? So if you initialize yourself in one of these wells, or in a superposition of these wells, they will dephase.
So now you're looking at the classical energy with a transverse field. Those states.
Yeah. Mm-hmm.
And you're making statement about eigenstates.
Yeah, of the German model.
The previous part of your talk was about channels and the dynamics.
Yeah, so this is very.
Okay. So I thought you were going to talk about partition sums, at least quantum partition sums, but you're just talking about ground states here.
This is basically telling you what you could talk about, but that I'm not going to talk about.
Okay.
So that's really the point of this. Okay, there's interesting things even if you put them into a transfer field, but this doesn't give you what I want to have.
Sure.
So and actually the method in the end you use the same bounds, right? Because you want to basically show that kind of two states in this well. And this well will not hybridize by introducing this guy, right? And in the end, the calculation is more or less very similar, actually. But it's not gonna what I'm going to be interested in.
Sure.
Yeah, this is actually why I'm saying this. So models that I'm interested in should be quantum memories. And how do we get there? Okay, instead of taking transfer field, what we will do is we will do products. Okay, I already said that I think 3 times, right? You should always hammer it in. And what we will do is that we will do a Cartesian product. And what does it mean? For example, one example that I already alluded to earlier is that the fact that the toric code is the product of two 1D Ising models or 1D repetition codes. So how does it know? Okay, let's do it. So we take an input code which has bits and checks. Right? The Ising model, right, is a chain of bits, and you have nearest neighbor parity checks. Two-body interactions. So the graph looks something like this. You have just alternating bit check, bit check, bit check. Now you take 2 of them. Cartesian product, right? You take 2 bits of the bits and checks. And then you will have 4 different kinds of 2 bits. You have double circles, double squares, and then 2 kinds of circle squares. Well, now you say, oh, a circle square, right, inherits a connectivity both from the input square and the input circle, right? So this circle square comes from this square and this circle, right? So it's connected to this square, to this circle, and to this circle, right? So it's really just you take the tuples and you connect it to anything that was connected originally. And well, now what you do is you say, oh, so circle, and square will be qubits. And now the 2 different mixed things will be X and Z checks. And then you get the toric code in its rotated variant, for example. So this is really all the magic there is. And obviously you can now do this prescription that I told you, right? So here it's very visual and simple. You can do this for any kind of bipartite graph, right? And you can do the same identification. And this is really what we are going to do. But now for the more complicated spin models that are spin glasses. Right? And in general, you can show, okay, here first we go from an L1L code, right? 1 classical bit, distance L, to a L squared 2L code. And you see already the problem, right? And this is why the thermal stability stays the same. It's because the distance, right? The number of qubits grows, right? You square the number, but the distance stays the same. So that's the problem. And in general, what you get if you take kind of the code, the product of a model with itself, you get something that is n squared, then proportional to Quay squared. There can be a prefactor here, which depends on the details. And then there's d stays the same as in the classical model. So we won't be able to save the linear variance, at least not in this trivial way. What I should say is there are ways to save the linear barriers, but they are more complicated. So I won't, you can ask me later if you want to learn about that. But there are good quantum codes, and then you have to take products and factor out the symmetry, or take products of free modules. And okay, so I already flashed the slide. So what you now can do is you take two products of a good code, for example, right? And then you get something that is n square root n. Yeah, I don't really know what to say about that. So yeah, okay. But what is also important,
So it has order n spins, order n physical, qubits or whatever, order n logical, barrier square root of n.
Yeah.
Okay.
So the barrier I haven't told you about, just about like the kind of operator that takes you from one ground state to the next is size.
Square root of n.
Square root of n, right? I haven't tell you anything about energy barriers, but this slide tells you now that also the energy barrier is actually inherited. And actually, this is generically true. There's proofs of that. I should put a reference there for you. Okay, so these papers prove that if you take the product of two codes with linear confinement, the output quantum code will actually have a variant of that. So in homology, this is called a boundary and co-boundary expander, just for those who might have heard these terms. What does it really mean? Is you look at eigenstates. So now, right, so what states do we look at? So what we look at is eigenstates. And these eigenstates, because it's a stabilizer Hamiltonian, we can basically think of the eigenstates as, oh, you start from some ground state, for example, which is all the stabilizers fixed, and then we apply Pauli operators. And this should be an X and a Z, right? Some Pauli strings, and you can basically label all eigenstates by kind of bit strings. By what's the Pauli string that you have to apply to get from the ground state to that eigenstate. And then what you can show is that the energy of the eigenstate, right? So this is actually if you have an eigenstate, this has energy HZX and HXZ, and HX and HZ are some parity check matrices defined by the product in some way. So these are the checks. And then the energy kind of depends on the size of the operator that you have to apply. But of course now, what if I apply a stabilizer? Nothing changes at all. So obviously it can't just be the Hamming weight of the operator. So what you have to do is you have to use some reduced norm of these things. And the reduced norm is actually, you asked about the smallest representative that has the same action on the ground state. So you minimize basically over multiplying all the stabilizers. You have to do some minimization, which is hard. These things are hard to calculate in practice. But what you can show is, okay, you go from the ground state to an eigenstate with some operation, and the smallest operation you can use lower bounds actually the energy increase. That's it. But this is only true for these models out to square root n. So what this means is that these models still have a linear barrier, right? If you apply an operator from on the ground to the ground state, the energy has to increase, but only up to an operator to the square root of n. And it's a bit of a nuisance, but it turns out this is still enough. But then you have to work. So this is actually probably most of the work of this proof is probably that part, where you show that this still implies some finite energy barrier. But okay, you can do it. And actually, I should say here, there is a paper by Andy Lucas and Yifang Hong and collaborators, which proved kind of stability of the ground states, which was very helpful. So stability of the ground state was known before, and we generalize this then to the arbitrary energy states, so to the local minima basically. So there's a lot of work going into this. Okay, you can do it, and I won't talk about it here. And then this is basically what gives you 1 and 2. So now you know, okay, even with square barriers, you have stability, and you can again count the counting, and you know that there's more local minima than global minima. So the only thing left to do actually is to show that typical Gibbs states are not separable. So they are long-range entangled. So you do that, and well, the intuition, of course, is okay. These are error-correcting codes, so they should be long-range entangled. And actually, there's it turns out there are rigorous statements that tell you that. In particular, there's a great paper by Sergei Bravi, Lee, and Yoshida, which says that ground states of quantum codes are long-range entangled. Great. So the ground states, we know they're entangled. This is a code. But of course, we want to make a stronger statement. You want to make a statement about kind of some partition sum, right? So some density matrix. And this is trickier. So what do you do? So what you do actually is technically, okay, so you have basically, you have an energy landscape like this. But now, of course, when I draw this, right, this is really a bad drawing because when I mark, for example, this blue minimum here, then what I really mean is this is some subspace of a high-dimensional Hilbert space. And the Gibbs state that lives there is like the global Gibbs state, e to the minus beta h, truncated to that subspace. This is really what it is. Now, what I cannot prove, and that's kind of not true a bit, is that this subspace actually does not contain short-range entangled states. So the whole subspace is actually completely devoid of any states which are short-range entangled, which can be prepared by a finite depth unitary. And then, of course, it follows. And how does it follow? Basically, what you show is, look, if you look at kind of the top-down view of the landscape, you have a subspace like this. And this subspace has copies that are symmetry equivalent because I have many ground states. And of course, all the spectrum is kind of 2 to the k fold degenerate. So also the subspace has kind of copies that are related by logical operators. And then what you can show is that you can take basically one state from each of these subspaces, and these states together form a code again. So it turns out even from the middle of the spectrum, even superpositions of eigenstates. So this is not a statement about eigenstates. This is about a statement about arbitrary superpositions of eigenstates from this subspace, right? And this subspace is the span of eigenstates. But any state in this subspace, which can now be volume law entangled, whatever, right? You can in principle use to define the high distance code. And then by known theorems, which are actually also recent, so these are recent results, you know that there must be a long-range entangled. Okay, so this is maybe technically how you get there, but what is actually really, I think, a quite remarkable statement is that, okay, you have this landscape here, and if you think of it, there's a subspace here, and the subspace is completely devoid of trivial states, right? So even at finite temperature, this is somebody supported on a subspace which is topologically non-trivial. And in that sense, it is in this sense that the models are topologically ordered. Oh, 3 minutes. Huh, that's very good, because I have one slide left, which is this one. And this is numerical experiments. So can you do it? Well, you can do it numerically, and you can look at examples, which, and okay, the example that I'm actually using here is not the example that I told you about, but one of the examples where you model out a symmetry, because otherwise, actually, the number of qubits grows enormously because you have the square.
So what do you model?
So I do now numerics on some model. I will not tell you the one.
How big?
Oh God, this I think is 60,000 qubits. So this is a stabilizer simulation, so, right? So it's a stabilizer model, so you can actually do numerics.
Okay.
But so if you do like actually the hypergraph plug and you want to do piece in glass and so on, you get like to 1 million qubits very fast. So this is why you use actually some other construction, but it has the same properties. And yeah, then you can basically do heating and cooling. And what you see is, okay, that if you start in a ground state and you heat, so this is some Gibbs sampler, which kind of samples the Gibbs distribution, you see that there's a sharp transition where you kind of thermally, the ground state is stable, and then at a distinct temperature, it kind of recovers the thermal equilibrium. And so this is kind of the threshold of the code in some sense, unlike passive correction, this is some critical temperature. And then if you cool it, then actually you see that you get stuck. And this is more or less independent on the cooling rate. But instead you get stuck in one of these local minima. And okay, what is well known kind of is the fact that these two timescales, I mean, well known, classical models also have this, that actually the temperature scale on which you get stuck and on which the ground state is stable, these are distinct. And this corresponds to a phase-time like this. At high temperature, you are kind of trivial. So you have one ergodic component. And then at low temperature, it's shattered. You have many components. They're all separate and they're all small. And then there's intermediate regime where you have one big ergodic component, which kind of incorporates most of the mass of the equilibrium state. But they are special states. Maybe in quantum theory, maybe we'll call it scar states or whatever. But it's very different, right? Because it's not eigenstates. It's like ergodic components. But there's very special initial states, like the code words, which are still stable. So it's kind of weak ergodicity breaking. Yeah, and these are two temperatures, and you can roughly determine from the marries which are to show this. And yeah, with that, let me summarize. Okay. So the first thing is, okay, I showed you that you can actually, which is kind of also remarkable, you can rigorously prove. So all the statements that I made basically are rigorous. If you actually look at our paper, the theorems and so on. So I spared you that. But you can rigorously derive kind of classical spin glass order actually directly from basically statements in computer science, which is already pretty nice. But then if you go to the quantum setting, then actually you get quantum linear confinement. You get actually something that, to the best of knowledge, hasn't been seen before, which is something we call topological quantum spin glasses, where you have kind of many local minima, but they are all topologically ordered. And also along the way, we actually generalized the Markov chain bottleneck theorem to channels, which is independently interesting. So, okay, thank you very much.
Questions? I have any. You mentioned that